Hello. We have been discussing calculus of variations and its applications in mechanics as well as structural design or optimal structural design, and we are looking at nuances of calculus of variations where we consider general boundary conditions that led us to this Weierstrass-Erdmann corner conditions where we have functions that are non-smooth. And then we also looked at invariance and Noether's theorem, which talks about transformation of the variables in a calculation problem, and how if there is a parameter there is something that is constant that in the case of mechanics gave us the conservation of energy, conservation of angular momentum. These two things we did. Similarly, you can also do conservation of linear momentum with a parameter in Noether's theorem that alpha is a translation as opposed to being a rotation. That is what we did. Today we are going to look at calculus of variations, a slight variation in its theme to apply to what are called eigenvalue problems, something that is about free vibration. So, principle of minimum potential energy is only for statics. Now we are going to move to free vibrations, and we also discussed Hamilton's principle, that is for dynamics in general. Okay. So, we start with again a very simple example, and that is always one dimensional, and in this case a one dimensional example is a string, a musical instrument. It will vibrate, it produces pleasant sound, that is to do with the frequencies and mode shapes of the string. We look at that in the framework of calculus of variations today. So, let us consider a string. So, what we consider here today is free vibration problems, free vibration problems in the framework of and specifically of strings that are taut, meaning that in tension, using the framework of calculus of variations. So, let us take a string that is kept taut between 2 points. Okay. It can be a pin joint also, does not matter. For a string does not have any bending strength, in the sense that if I apply a force here, a string is going to deform like this. It does not bend like a beam does, it just goes like that. Okay. Now, so that is why we can show whichever way we want. Between 2 points we have a string, okay, and there is tension in it. There is a pretension equal to T. Let us take this length to be L. A string that is length L, tension T, and the material property that we would need here is density, mass density, denoted by rho. Okay. So, now we will actually define this rho as kilogram per meter, cross section, unit cross section. So, we will take it density like that way, linear density, kilogram per meter as opposed to kilogram per meter cube. If you have such a thing, we want to write the governing equation for it when we pluck it. Let us say somebody comes and plucks it, something like moving it over there, then for the moment it will become like this, right, it will become like that, and then it starts vibrating in some way. It may vibrate like this or like that or many which ways. You have a string, you are perturbing it basically. Okay. So, how do we write equations of motion? We use calculus of variations, which is to say that we extremize, this is optimization, but we do not commit to minimization or maximization. That is what Hamilton's principle tells us. Extremize, what do we extremize? The deformation wherever it goes. Let us call this W of x. As usual, x is measured along the axis. Here x equal to 0, here x equal to L. okay, extremize with respect to Wx. That is a function as usual in the calculus of variations. What do? We have this action integral, which is integral of Lagrangian with respect to some time t L dt. And what is L? That is our Lagrangian, which is kinetic energy minus potential energy. Okay. What is kinetic energy for a vibrating string? So, we take a little piece wherever that is vibrating, it is a dx. Okay. Whenever there is a dx, we have to integrate from 0 to L the kinetic energy of little thing as it vibrates by the W there. Okay. So, when that we have that, then we can write it as half into mass per unit length. Okay. That times dx, rho dx will give me the mass. I have to put mv square, half mv square. Now, I have half m, I have to put v square, that I will put as w dot square, because w is the transverse displacement. When I say w dot, what I mean is dw by dt. Okay. This is not omega, okay, this is w dot is dw by dt, that is the kinetic energy. Okay. Now, let us also write the potential energy, that has two components, strain energy plus work potential. This is with the internal energy stored in an elastic body, string is an elastic body, and then external force. Since we are talking about free vibrations, this is not there, that is equal to 0. That is a negative of the work done by external force, that is equal to 0. For the internal force, we have the tension T, and how much it is stretching is what we need to put. So, when we have a string and when it stretches, okay, let us say I have this string, when it stretches in some manner, okay, that is our Wx, that is our Wx everywhere, again x goes from 0 to L. So, what is this length? We know the length of this equal to L before stretching. What is the length of this curve? Okay, this is the changed length. The difference of these two times T will be the strain energy or internal energy stored in the string. To get this changed length, let us take a little element somewhere as usually do, that is ds. That ds is Pythagoras theorem square root of dx square plus dw square. Okay, that is this portion, that is dx, this is dw. Okay, I mean that is too small to see, let us blow it up. So, if I take this as a ds this way, this is dx, that is dw, that is ds. Okay. So, now this can be, by taking dx outside, I can write this as 1 plus dw by dx square dx. So, I can write my strain energy here as 0 to L, the little thing, how much work, how much is stretching, that I will write, that is I will do square root of 1 plus dw by dx square dx minus L, and this whole thing I want to multiply by my tension T in the string. Okay. That would be the internal work or our strain energy. Okay. Now, we are going to approximate this because W is going to be small, the small vibrations. Square root of 1 plus dw by dx square for small slopes or small vibrations, we can approximate this as half dw by dx square. Okay. Square root of 1 plus x for small values of x is equal to 1 plus, in this case the 1 will become dx and it will cancel L. So, when I say I am approximating it, this is 1 plus this times dx. I am approximating only this portion. Square root of 1 plus x square is equal, or 1 square root of 1 plus x can be approximated as half of x plus 1. Okay. Now, dx is there. When you do this integration, that will lead to L. Okay, when you integrate it, that will lead to L, that will cancel this L. So, our strain energy turns out to be 0 to L half, and then we have the T there, T into dw by dx square dx. Okay. Again, when I integrate to 1, that leads to L, that L cancels this minus M, they cancel each other. So, I have the strain energy and potential energy. Again, let us recall the potential strain energy, kinetic energy that we have written is over here, and now we also have strain energy, which in this case is also equal to potential energy. Okay. Now, we can write our Hamilton's principle. Okay. So, what we have is that action integral is kinetic energy minus potential energy, which is equal to strain energy. Here we write kinetic energy 0 to L half rho w dot square minus half T w prime square. So, w prime is dw by dx. This whole thing over dx is what is action integral. Okay. Now, once we have this, we write our Euler-Lagrange equation. So, our integrand, this thing is our integrand f. So, what we write is dou f by dou x minus, sorry, not x, this will be dou w, dou f by w is our variable, right, when we are extremizing this, okay, with respect to w of x, dou f by dou w minus, since we have two variables, okay, one more thing, this is just L, we have to do this from 0 to action integral is 0 to t, sometime t, Lagrangian dt. So, we have dt also, we have two independent variables x and t. So, we get dou f by dou w and then dou by dou x of dou f by dou w prime minus dou by dou t of dou f by dou w dot equal to 0. Okay. We have a function, now w is a function of just x, it will be x and t. Okay. That is what I mean, we can say for aberration things are varying with time and space. Okay. So, I think let us go back and change. If I wrote w of x here, this is x and t, this function of x and t both are variable. Okay. That is equation. So, let us write it now. So, what we have dou f, that is anyway 0 minus f is there. So, dou by dou x of dou f by dou w prime, there is already minus here. So, that minus t, the 2 and w prime square in here they cancel. So, I get w prime minus dou by dou t of again half and 2 in omega dot square will go, there will be rho not omega w dot, that will become rho w dot equal to 0, or what we get is here minus of minus plus, we get t w double prime, okay, and over here oh okay, I think the sign we forgot about one thing. We had strain energy that we have written w and the the T times the change in length, that is our strain energy. So, we have potential energy there minus, okay, seems fine, let us see, okay, T W double prime, and then we have minus rho W dot W dot equal to 0, okay. That is what we get. We get T W double prime minus rho W double dot equal to 0, okay. So, this is our governing equation, okay. Now, in order to solve this, we assume separation of variables, meaning we will assume that W x comma t has separate space part, that is x part, and then the time part, okay. If you do this, W prime will become phi prime q, because only this has x, this does not. Similarly, W double prime will be phi double prime q. Similarly, W dot will be phi q dot, because only q is a function of time. Similarly, W double dot will be phi q double dot, okay. If you substitute these results into it, what we get is T phi double prime q minus rho phi q double dot equal to 0, okay. I have substituted for W double prime this one over here, and for W double dot for this one over there, okay. So, this gives us this result. So, we get T phi double prime divided by rho phi equal to q double dot by q, okay. We basically from here we arrange them so that things that depend on time are taken to the right hand side, that is q and q double dot are the ones that depend on time. Things that depend on space, phi double prime and t are on the left side, and given constants, tension in the string T and mass density, linear mass density, that is mass per unit length of the string is rho, they are on this side. So, if you look at this particular thing varies with x, this particular thing varies with time, right, but both are equal. What this means is that this must be equal to some constant, because we have two things, left hand side is dependent on space, right hand side is dependent on time, and they are equal. That means that whatever quantity that is equal to cannot vary with space, that is x, cannot vary with time, that is t. So, that is what we have. This one for convenience we call it minus lambda, even if you take plus lambda nothing happens, you can still arrive at the same conclusions, but making it minus helps us, because that lambda turns out to be what we call natural frequency of the system, okay. That is free vibration, there will be frequency, that is what we get, rather square of that, okay. So, what we have here, when I assume minus lambda, I get two equations here from this. One is T phi double prime, that is minus lambda rho phi, when it comes to the other side become lambda rho phi is equal to 0, and here q double dot plus lambda q equal to 0. Again notice the minus sign, okay. We get two equations, this is all for space, this is for time, because q we assumed in the separation of variables that this part depends on time, this part depends on space, okay. So, if you look at this equation, that let me write again, q double dot plus lambda q equal to 0, there are many solutions for it. So, both sine and cosine depending on the initial conditions that you have about q, you have many solutions, right. For example, if I say q equal to sine n pi, okay. If I say sine n pi t, okay, then q dot is n pi cosine n pi t, and then q double dot is equal to n square pi square back to sine with a minus sign n pi t. Okay. Now, if you substitute this back here in there, substitute there, q double dot minus n square pi square sine n pi t plus lambda, what is q? Sine n pi t, sine n pi t, that is equal to 0. Then you find that this lambda is equal to n square pi square, that is when it will be 0. So, that is that lambda is equal to n square pi square, or you could have assumed the square root of lambda is n pi, or square root of lambda is n pi, where n can be 1, 2, 3 up to infinity. So, there are, when I say many solutions, there are infinite solutions. I can assume n equal to 1 to infinity, I have that many solutions. Now, I taken this lambda, I can put back into this equation and solve for phis. Okay. Now, that we know many lambdas are there, so I take t phi double prime plus lambda rho phi equal to 0, where we know that this lambda is equal to n square pi square. For each value of n, I get to solve this equation for phi. So, lambda is our natural frequency and phi is our eigenfunction, or we can call this eigenvalue, and this is eigenfunction. Any word that has eigen as prefix has to be written together. Eigenvalue is not two words, it is single word. Eigenfunction, eigenmode, whatever you say is a single word with what follows, eigenfunction, or what we call in vibrations mode shape, natural mode shape or normal mode shape. Okay. We get all of those here. So, these phis, just like lambdas, we have lambda I, where this I goes from 1 to infinity, lambda I, and phi I, there are many one of them, infinite ones. Okay. And they all have special properties. What are those properties? That any two of these, let us say I take phi I and phi j, these are orthogonal. So, you know that when there are vectors, like in vector calculus vectors, let us say my finger is one vector, my pen is another vector, if they are perpendicular like this, we can say that they are orthogonal or perpendicular to each other. Okay. When two things are perpendicular, whatever one has, this does not have, whatever this has, this does not have, like x axis, y axis do not have anything in common except origin, of course. Okay. So, similarly for functions, when we can talk about two functions being orthogonal. What does that mean? Here this phi i's are functions of x. Okay. Phi I, phi j that we have, they are functions of x. When I take two functions phi I, phi j, two eigenfunctions, I would say that they are perpendicular to each other if this product is 0 for I not equal to j. Okay. Perpendicular. If I equal to j, then I can have a normalization as we call it. So, if I say phi I square, I will also multiply rho here. Okay. That is just a convention. Something is 0, does not matter if you multiply. I do this 0 to L to be equal to 1. This is the normalization condition, because mode shapes or eigenfunctions can be of any amplitude. what decides is the shape itself. This is normalization, this is orthogonality. When put together it becomes orthonormal. So, these two things are satisfied for these 5 functions, we call something orthonormality. Orthonormality. Okay. And you can also prove that these lambdas that we got, they need to be, they will be, not need to be, they will be only non-negative. Okay. That is, they will be either 0 or positive, they can never be negative. In order to see that, okay, let us take, remember this equation T phi double prime plus lambda rho phi, many times we will use this. So, we have T phi double prime lambda rho phi equal to 0. We will use this to prove that lambdas have to be non-negative. Okay. That we can see by taking this, multiplying by phi. I will take phi double prime, multiply by phi and lambda rho phi, another phi multiplying again, and take dx, integrate it from 0 to L. So, basically I have taken that equation, multiplied by phi and then integrated over x from 0 to L. Okay, that still be 0, nothing changes. Now, here in calculus of variations, integration by parts plays a big role. So, we will do integration by parts. So, we will do the first function as that one, integral a second function, that is that one, that will be that at the two ends, then minus derivative of the first function, this is the first function, that will become phi prime, integral of the second function, that is also phi prime. So, phi prime square dx plus we have this other part 0 to L lambda rho phi square dx equal to 0. Okay. Now, if you look at this quantity, since phi, which is our spatial function for the string vibration w, again remember that w, which is a function of x and t, we have taken it as phi of x, q of t, our separation of variables technique. So, whatever boundary conditions w satisfies with respect to x, phi will satisfy, whatever it satisfies with respect to time, q will satisfy. Our interest here is phi. So, when w is 0 at the either end, phi will be 0. So, at 0 and L, x equal to 0 and x equal to L, this actually goes to 0. So, we are left with this. Okay. Now, here we get something very important, lambda is equal to, we can write integral 0 to L t phi prime square dx divided by 0 to L rho phi square dx. Okay. You see this lambda now has no way of becoming negative because tension T is positive. See, if the tension T is negative, that is there is slackness, there is no tension, you cannot vibrate a string. So, tension is by definition positive, mass density cannot be negative. So, that is also positive, and then we have phi prime square in the numerator and phi square in the denominator. So, this tells us that this lambda is greater than or equal to 0. Any lambda, I just took arbitrary, if I put phi I lambda I, it will be true. Okay. So, this lambda that we got as a ratio, this has a name, and that name is Rayleigh quotient 0 to L rho phi square dx. This has a name that goes by the name Rayleigh quotient. Quotient is like a ratio. Okay. It gives you the eigenvalue. Okay. And phi is of course what we said, phi is eigenfunction. I can get lambda as a quotient, right. If it turns out that if you take phi anything, it need not be correct eigenfunction. You take any function that satisfies the boundary conditions. When you do it, you get a lambda value, and that lambda value is always larger than the real eigenvalue. Okay. We will come to that minimum characterization of the eigenvalue problem. So, there is again another optimization coming up. Okay. We will stop here and then continue, but know that we have this Rayleigh quotient, which is very important both in mechanics as well as structural optimization, as we will discuss. Thank you.